4-3, patterns and nonlinear functions. So our objective in this section is to identify and represent patterns that describe nonlinear functions. Last section we talked about linear functions, functions that make lines. This section we're going to talk about nonlinear functions, functions that don't make a line. Right. Just like linear functions, nonlinear functions can be represented using words, tables, equations, ordered pairs, and graphs. So a nonlinear function is a function whose graph is not a line or part of a line. Okay? So here are some examples. So my linear functions look like a line, look like a line, horizontal line, vertical line is okay. Okay? So these are all, the first three are all examples of a linear function, a function whose graph is a non-vertical line or part of a non-vertical line. All right, because a vertical line would not be a function. So a nonlinear function is going to be a function whose graph is not a line. So we have a nice curve here, which is actually a parabola. We have this curve here, which is a cubic function, x to the third power. And we have these dots here, which represent a almost a line, but a line that's sort of reflected where the negative part would have gone this way, but now that negative part is positive because this is an absolute value function, right? Everything that was negative gets flipped to the positive. Okay? So let's take a look at this first problem and decide which of these functions show us a linear function and which don't. So the area in square inches of a pizza is a function of its radius, r, in inches. The cost in dollars of the sauce of a pizza is a function of the weight in ounces. Graph these functions shown by the tables below. Is each function linear or nonlinear? So if we look at the first table, which is my pizza area, I'm going to graph A as a function of r. So if I were to graph this, I would make a graph. I'm not going to worry about negative numbers because pizza radius can't be negative. Okay, so that's going to be my r. 6, 8, 10. Okay. And then my area, I'm obviously not going to go by ones because I don't feel like making 314 dashes. Okay, let's go by 100. So let's call that 100, 200, and 300. Okay? So with a radius of 2, my area is 12. Very small. With a radius of 4, that's 50. 6, that's a little bit over 100, 113. And it looks almost straight until now we get to 200. And at 10, we get to 314. So you can see as we make this graph, it definitely is starting to curve up. And if you look at the difference between these two numbers, that's about 38-ish, give or take. That is going to be more. That's going to be about 63. And then, of course, another, is that about 87 and over 100 to get the next one. Okay? So because the differences between my outputs here, my inputs are always going up by 2, but my outputs are going up much faster as we go. That is non-linear. Right? Whereas the sauce, okay, we have the weight of the sauce and the cost. Okay, so the weight, let's go 2, 4, 6, 8, 10 again. Okay, and this one now we can go with $1, $2, $3, and $4. Okay. So you can see at $2 is 80 cents. $4 is $1.60 right in the middle there. $6 is $2.40 and right about there. $8 is a little bit over 3, and $10 is 4. And if I could draw perfectly, this would be perfectly straight. Okay? Um, so we can see that this is linear. Okay? Bad linear. There we go. And we can see that the difference between all these dollar amounts is always going to be 80 cents. So as I go up by 2 ounces, the price of the pizza always goes up, or the price of the sauce always goes up by 80 cents. That is a linear function. Okay? So here's our got it problem. The table below shows the fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. Start with the whole paper, cut it in half. Start with that piece, cut it in half, cut it in half again, cut it in half again. Graph the function represented by the table, and is this function linear or nonlinear? Well, I can tell that, right, after one cut, it's 1/2. Two cut, there's a quarter left, then an eighth, then a 16th. The amount left is getting smaller and smaller and smaller, right? If I went down a quarter here, now I'm going down an eighth. Okay, I'm not going down a quarter anymore. If I wanted to graph this, make a little more room. If I wanted to graph this, I would have 1, 2, 3, 4 cuts, and my area, let's just call that 1. That's going to be 1/2, right? 1/4. So you can see that we start at 1, then a half, then a quarter, then half of that, then half of that, and then so on. And you can see we get a nice curve that eventually gets flatter and flatter and flatter. And will it ever reach 0? And the answer is no, because you can always cut half of it. And the denominator will continue to get larger and larger and larger and larger, but it will never actually be 0. Now, of course, that's not realistic. You can't actually cut a paper infinite amount of times. Eventually, the piece of paper will be so small that you can't actually get your scissors to cut it. But for mathematical purposes, we can say that it's not possible. So the next question deals with representing patterns and nonlinear functions. So the table shows the number of total blocks in each figure below as a function of the number of blocks along one edge. So you see with 1 block, then 2 blocks along each edge, and 3 blocks along each edge. Okay? So for first one, there's 1 block. Now we have 1, 2, 3, 4, right? 1, 2, 1, 2, this block, this block, this block, this block, 4, and then 4 more in the back, so that's 8 blocks. Then we have 3 times 3 times 3, that's 27. And then 4 would be 64. So my ordered pair would be 4, comma 64. Okay. And 5, which I'm not going to even try to draw these things, would be 125 blocks. 5 times 5 times 5. So that's 5, 125. If you see the pattern there. Okay. So represent the relationship using words, an equation, and a graph. So each time I add 1 block, the total number of blocks becomes the cube of the number of blocks on one edge. So each time I represent 1 block to the left, I put another row back, and I put another row on top. So we're going to be multiplying, by the number of blocks 3 times. So to write an equation for that, it turns into y is equal to x to the 3rd power. And if I wanted to make a graph, this graph would actually get very big very fast. Okay, so if I wanted to make a graph, I would go 1, 2, 3, 4, 5. And that would be the number of blocks uh, on the edge, and this would be the total blocks. Okay, so for here, let's go up by 50. So this is 50, 100, 150, and you can see that at one block we have one, very little. At 2 blocks, now we have 8, still very little. 3 blocks, now we're jumping up to about halfway. 4 blocks, a little bit bigger than 50. 5 blocks, 125, so that's there. And then 6 blocks would be 6 times 6 times 6 would be 216. So if I were to do one more line here, you can see this definitely jumps up way higher to 216-ish. And we have a nice curve like that. So there's a representation of this pattern using a graph. Let's try a got it problem. The table shows the number of new branches in each figure of the pattern below. So we see we hit the first one, first pattern, we have 3 branches. Then every branch gets 3 more. Then every branch gets 3 more. What is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. Okay? So, to figure this out, I'm going to finish this table right here. So I can see that on the first one, the number of branches, or the number of the figure is 1, the number of branches is 3. Number of the figure 2, 9, 3, and I can count them all up if I wanted to, 27. So on 4, it would be 81, and 5 would be 243. So where am I getting these numbers from? Well, what I realize is that this one is 3 to the first. Right? I'm taking one branch and I'm multiplying it, and I'm making 3 times to it. This one is 3 squared, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9. This one would be 3 to the third. So the pattern here is going to be y is equal to 3 to the x power. So that would be 3 to the fourth is 81, 3 to the fifth is 243. And if I wanted to graph this, my graph again is going to get really big really fast. So 1, 2, 3, 4, 5. And that would be branches. Oh, sorry. This is going to be the figure number. And then this would be branches. Okay, and let's call that, let's call it 50 again. 100, 150, 200. Okay, and one branch is 3, very little, 9, very little, 27, about halfway, 81, almost to 100, and 243, suddenly we are going up very fast. Ooh, little hitch there in the graph, but it's okay. Okay. So with these nonlinear functions, you can represent them in a bunch of different ways. Okay. A function can be thought of as a rule that you apply to the input in order to get the output. You can describe a nonlinear function with words or with an equation, just as you did with linear functions. So here's some data. Input is 1, output is 2. 2, 4, 3, 8, 4, 16, 5, 32. What is a rule that represents this function? Okay, well, if you want to, you can think of this with a table if that helps you. So 1 gives you 2, 2, 4, 3, 8, 4, 16, and 5, 32. And I gotta figure out a rule that works for not one of them, but all of them. So let's try the simplest one. That y, if I'm starting with x, how about that? Well, okay, works for the first one, right? If I plug in x, I add 1 to it, I get 2. But if I plug in 2, add 1 to it, I get 3, not 4. So, no good. So I got to come up with a different rule. Okay? And this is just you get a little bit, but first of all, I noticed that this is nonlinear, so this one was never going to work. Okay, so I could try something like this, but again, that is a linear function as well. Right? We'll see that a little bit more next chapter. But if I plug 1 in, that works. That's 2. If I plug 2 in, that works. That's 4. If I plug 3 in, that's 6. So it doesn't give me 8. So this one is no good as well. So the trick is to come up with a nonlinear function that makes all these different points work. And there's no trick to this. It's just realizing that each successive y value is the previous one multiplied by 2. So 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So the way you continue to multiply 2 by itself is to give it an exponent. This equation, let's check. Does it work? 2 to the first is 1. 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16. And 2 to the fifth is 32. So let's look at our got it problem. And when we look at this one, we're going to have a very similar situation. Okay? Actually, never mind. This one is a little easier. So if I look at my table, I have 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25. Okay? Well, you can put in that y is equal to x to make the first one work. That's not true for all of them. We could try to guess other things, but I would notice that if I take 1 times 1, that's 1, 2 times 2 is 4, 3 times 3 is 9, all of these on the y on the output value are perfect squares. So I can simply make my equation as y is equal to x squared. Okay. So let's look at our lesson check right here and graph the function represented by the table. Is it linear or nonlinear? So x is going up by 1, y is going up by 1. This is a linear function and pretty simple to graph as well. The ordered pairs 0, -2, 1, 1, 2, 4, 3, 7, and 4, 10 represent a function. What is the rule that represents this function? This one I want to go through. So in order to solve this, let's make a table. X, Y. Okay, this is just to help you see it a little bit better. Okay, 1, 1, 2, 4, 3, 7, 4, 10. Okay, if you notice, these are all have the same difference, right? To get from one to the next, all of them go up by 3. So this is going to be a linear function. Okay, so that means y is going to be some number times x, and then maybe plus or minus something. Well, because this difference is 3, we can say that y is equal to 3x. But if I plug 0 into there, 3 times 0 gives me 0, not -2. So maybe I should subtract 2. And let's see if that works. Plug in 1, we get 3 minus 2 is 1. Plug in 2, that's 6 minus 2 is 4. And yes, it does work. Which rule could represent the function shown by the table below? So again, if I wanted to try to solve this, I got to figure out which one of these, and they give you choices here, A, B, C, which one of these functions actually works. Okay, so 0 squared is 0, -1 squared is +1. That's out. -1, 0 to the third is 0, make it negative, it doesn't matter. 1 to the third is 1, make it negative. 2 to the third is 8. So that one doesn't work. So my answer is C. For 4, does the graph represent a linear function or a nonlinear function? That's a linear function. It's a line. That is not a linear function. It's not a line. And finally, classmate says the function shown by the table on the right can be represented by the rule y is equal to x plus 1. Works for the first one. Works for the second one. It does not work for this one. Okay, so if you notice here, the difference here is 1. The difference here is not 1. And there's going to be a different difference each time. So this is not a linear function. So it's just a matter of trial and error. And the thing I notice is that each one of these is 1 bigger than a perfect square. So my rule would be x squared plus 1. Okay? Kind of hard to pick out, but with a little practice, you'll get used to it. Okay? And that's 4-3, patterns and nonlinear functions.